the distinction between combined TSA and sum of individual TSAs. Hello everyone. Today, we are going to tackle a topic that often trips up even the most diligent geometry students. As we begin our introduction, I want to highlight that one of the most common conceptual hurdles you will encounter in geometry is understanding how surface area behaves when two or more solid objects are joined together. When you look at a complex shape made of multiple parts, a very frequent mistake is to assume that the total surface area, or TSA, of that combined object is simply the sum of the total surface areas of the individual components. It feels intuitive to just add them up, doesn't it? However, I must warn you, this is mathematically incorrect. In this tutorial, we are going to dive deep into the logic behind this. We will explore exactly why the contact area, the place where the shapes meet, changes the calculation, and more importantly, I will teach you how to correctly identify which surfaces to include so you can accurately calculate the surface area of any combined solid. The concept of exposed surface. Now that we've established the common mistake of simply adding individual surface areas, let's take a step back and look at the fundamental concept. To truly understand how to calculate the surface area of a combined solid, we first need to be very clear about what surface area actually means. Think of it this way. Surface area is strictly the total area of the exterior faces of an object. To make this more intuitive, I want you to imagine you have been tasked with painting a solid object. When you pick up your brush, you can only apply paint to the parts of the object that are exposed to the air. If a part of the object is hidden, tucked away, or pressed tightly against another surface, your brush simply cannot reach it, and therefore, that part doesn't get painted. So, applying this logic to our geometry problems, in mathematics, only the exposed surfaces, the parts you could paint, contribute to the total surface area of a combined solid. Keep this painting mental image in mind, because in the next slide, we are going to see exactly how this principle applies when we join two shapes together. The problem with adding individual TSAs. Now, let's look at why the mistake I mentioned earlier actually happens. When we calculate the total surface area, or TSA, of a single, standalone solid, like a cylinder or a cone, our formula must account for every single exterior part, which includes the area of its bases. For instance, let's look at a cylinder. The formula for the TSA of a cylinder is the curved surface area, or CSA, plus the area of its two circular bases. Similarly, if we look at a cone, the TSA of a cone is the curved surface area plus the area of its one circular base. However, here is the critical part. When we join two of these solids together at their bases, those specific circular bases are no longer on the outside of the object. They are pressed together, meaning they become internal faces, or what we call contact areas. So, if you were to simply add the individual TSAs together, you would be making a mathematical error. You would be incorrectly counting the areas of those faces that are now hidden inside the object, effectively counting surfaces that are no longer part of the exterior. In the next slide, we'll use a real-world example of a toy to see exactly how this looks in practice. Real-world example, a decorative toy. Now that we understand the theory behind exposed surfaces, let's put this into practice with a real-world example. Imagine you are looking at a decorative toy. This toy is made by joining two shapes together, a cone and a hemisphere. Both of these shapes share the exact same radius, which we will call r. To form the toy, the cone is placed perfectly on top of the flat, circular base of the hemisphere, so they fit together seamlessly. To see why our previous discussion is so important, let's perform a step-by-step analysis, starting with what we call the incorrect approach. In this first step, let's pretend we are making the common mistake we discussed in the previous slides, simply adding the individual total surface areas together without considering the contact area. First, let's look at the hemisphere. The total surface area of a hemisphere is equal to 3 pi times r squared. It is important to remember that this formula includes both the curved top and that flat circular base. Next, let's look at the cone. The total surface area of a cone is equal to pi r times L plus pi r squared. Again, this formula accounts for both the curved side and the flat circular base. If we were to follow this incorrect method and simply add these two values together, our sum would be 3 pi r squared plus pi r L plus pi r squared, which simplifies to a total of 4 pi r squared plus pi r L. As you can see, this number is quite large because we are still counting those two circular bases that are now hidden inside the toy. In the next slide, we will see how to correct this by identifying the contact area and finding the true surface area. Real-world example, a decorative toy continued. First, we need to identify the contact area. Think back to our definition of surface area from the previous slide. It's only the parts you can touch or paint. When we place the cone directly onto the hemisphere, the circular base of the cone and the circular base of the hemisphere are pressed tightly against each other. Because they are touching, these two circular faces are now hidden inside the body of the toy. They are no longer part of the exterior. This brings us to step 3, where we calculate the actual combined total surface area using the correct approach. Since those bases are no longer visible, we only sum the surfaces that remain exposed to the outside. For the hemisphere, we no longer use its total surface area. Instead, we only use its curved surface area, which is 2 pi r squared. For the cone, we similarly only use its curved surface area, which is pi r L. When we add these two exposed parts together, we get our total surface area for the toy, 2 pi r squared plus pi r L. To conclude this example, look at the difference between our incorrect sum from the previous slide and this correct total. The difference is exactly 2 pi r squared. This represents the area of the two circular bases that disappeared from the outside when they became the contact area. Now that we've seen why simply adding the individual total surface areas leads to an incorrect result, let's move on to step 2 and find the correct way to calculate this. As we move to the next slide, keep this distinction in mind, as it will help you avoid the most common traps when solving these types of problems. Common mistakes to avoid. First, watch out for what I call the formula trap. It is very tempting, when you see two shapes, to simply grab your standard formulas for total surface area and plug them in. However, as we saw with our toy example in the previous slides, blindly applying these formulas will lead you to an incorrect answer. Instead of relying on memory alone, I want you to pause and ask yourself a critical question. Which faces are actually visible on the outside? If you can't see it or touch it from the exterior, it shouldn't be in your calculation. Next, be very careful with overcounting. This is a subtle error that many students make. When two solids are joined, remember that it isn't just one surface that disappears. It is actually two surfaces, one from each shape, that are pressed together and hidden from view. If you only subtract the area of one base, your final answer will still be too large. Finally, a very important distinction to keep in mind is the difference between volume and surface area. It is easy to get these two concepts confused. Remember, volume is additive. If you melt two shapes down and combine them, the total volume is always simply the sum of the individual volumes. But, as we have demonstrated today, surface area is not additive because the contact surfaces are no longer part of the exterior. Now, as we approach the end of this lesson, I want to pause and highlight some common pitfalls that students often encounter when tackling these types of problems. Keep these points in mind as we move to our final slide to summarize our key takeaways. Key takeaways. All right, we have reached the end of our tutorial, so let's bring everything together with some final key takeaways to ensure you've mastered this concept. First and foremost, I want you to memorize this fundamental principle. The total surface area of a combined object is not equal to the sum of the individual total surface areas. If you remember nothing else from today, remember this. Next, let's revisit the term contact area. As we used in our example with the toy, the contact area refers to those specific surfaces where two solids are joined together. Because these surfaces are pressed against each other, they become internal. Therefore, they are never, under any circumstances, included in the calculation of the total surface area of the combined solid. This leads us to what I like to call the golden rule for geometry problems. When you are faced with a complex, combined shape, do not blindly reach for the standard TSA formulas. Instead, look at the object and sum only the curved surface areas of the components, and then add any remaining flat surfaces that are still exposed to the outside. To wrap this all up, I'll leave you with a logical formula that you can use to check your work. You can find the combined total surface area by taking the sum of the individual total surface areas and subtracting 2 times the area of the contact surface. We subtract it twice because, as we discussed in our common mistakes slide, one surface from each shape is being hidden from the outside. If you can apply this logic, you'll avoid the most common traps in these types of problems. Great job today!